ODE. Are we talking about literature? Are we going to be studying poems? Well, not quite. Of course, this is a calculus course, so we'll be looking at ODEs, not as odes, but as I said, ODEs. We need to spell it out because it's an acronym. So first of all, I'm going to explain to you what those three letters mean, and I'm gonna do that in reverse order because I think that actually that clarifies a little bit more easily what this expression stands for. So let's start from the E. What does the E stand for? It stands for equation. So an equation, of course, is an equality between two expressions. Nothing new. It's just an equation. Well, sort of like the ones you've seen before, but different. Different in what way? That's the second letter. It's a differential equation. That means it's an equation that includes one or more derivatives. Not only that, but it's an equation where the purpose is not to find the variable x, but it is to look for the original function, the one that gave rise to the derivatives. So you can start seeing the connection with integrals here. In an integral, we are given a derivative, and we're asked to find the original function or functions. In a differential equation, we're also given the derivative, but not straight out. We're not told explicitly what the derivative is. We're told something about the derivative through an equation. And from that, we have to try and figure out what the original function is. What about the O? This is the strangest one of the three letters because O means ordinary, but ordinary does not in the sense of common, everyday, routine, bourgeois. It just means that it's an ordinary differential equation because the function we're looking for has a single independent variable. Now, you may remember that we talked in the previous course about functions of several variables, and when we're dealing with functions of several variables, then we can compute partial derivatives. Well, there are such things as partial differential equations, which are the ones involving functions of several variables and their partial derivatives. They're a lot of fun, they're very useful, even more useful than the ordinary differential equations we're going to see here, but we're going to have to wait for next year to study those. So here is an example, for instance, of an ordinary differential equation. First of all, notice that it is an equation. It has an equal sign. Okay, so the fact that there is an equal sign makes it an equation. There is an expression on the left, an expression on the right. It is a differential equation because there are derivatives. There is a first derivative here, and there is a second derivative there. Right? There is also the function, but that's not required. You can have a differential equation without having the function explicitly mentioned, or even the variable. Right now we have an x in there. That variable doesn't have to be in there. So the equality and the derivatives are the two essential elements. It is an ordinary differential equation because we only have one single independent variable. Let's have a look at some terminology having to do with ordinary differential equations. Well, first of all, solving an ODE means finding all functions that make it true, sort of like solving an equation does in general. The general solution of an ODE is the set of all its solutions. Okay, so it's sort of like an indefinite integral, right? By the way, of computing an integral, once again, is a way of solving a very simple ordinary differential equation. Okay? I'm going to leave that to you to figure out what differential equation that would be. The one thing that may be a little bit different is an initial value problem. An initial value problem is an ordinary differential equation with some additional conditions that are satisfied by only some or only one of the solutions. This is sort of what we did again with indefinite integrals, where instead of asking for just the indefinite integral, we also ask, well, we want a function whose derivative is this and such that blah blah blah. In that situation, what we're looking for is the value of c that comes out of the indefinite integral. So computing the value, computing a specific antiderivative of a given function is basically an initial value problem. And finally, the order of an ODE is the order of its highest derivative. Okay, so in the previous example, I showed you a differential equation which had both first and second derivatives included, so that would be a second order differential equation. In this course, we're going to mostly be working with first order differential equations. We're going to see second orders only in very special cases. Next year, once again, you're going to be going to second order and maybe even higher if you're lucky. Why do we want to study ODEs? Well, quite simply because they're used to solve problems in where? Astronomy, thermodynamics, Newtonian physics, particle physics, biology, medicine, computer science, defense, and I'm sure I could make the list longer. You name it, there is one application. So the whole world revolves around differential equations. In fact, differential equations are really the core content of all of calculus, the place where calculus comes in and shines and makes its relevance known. In this course, once again, we're going to see very few of these applications. I'm going to show you some in the next few slides, but again, there is way more than what you're going to see now. And in fact, I could safely say that pretty much all of applied physics is made up of differential equations.